Okay, so chapter 15 is actually very easy. What we have talked about yesterday. Okay, yesterday we have talked about what is a continuous random variable and what is a density function. And for two conditions that can become a density function, the first thing is the whole graph needs to be above or equals to 0. And the second condition is the area under that curve must be 1 with the given domain. And also I have emphasized that when you sketch the density function graph, when you're trying to sketch it, or the question asks you to sketch it, you not only need to sketch for the domain, you also need to sketch for the rest of the part, which is y equals to 0. You need to show y equals to 0. You need to really use your pen to sketch it on the x-axis. That's the two things I emphasized yesterday. So first, how to prove there's a density function. Second, how to sketch the density function curve, which is a hybrid function. And the third thing we have talked about is how to find the how to find the probability for an interval, like for in between A and B, for greater than B, less than A, like those kind of things. And I said you use the area under the curve to represent probability, and that can, whatever your integral value find out, you should have your probability here. And yesterday we have done example 1 together. And I asked you to do example 2. Well, I don't think there's much problem with example 2. For A, like a lot of you don't know how to sub values, like make some calculation mistakes in that one, but in the end I think most of us figured that out. 2 is just a cast question. We all worked that out. For number 3, you need to be aware of your domain. Okay, this question is the question that most of you not did that well, because the domain is given to you is 1 to E, which E is 2.7, 2.718, like I don't know whether it's correct, about 2.7. But look at this one, that gives you 2.8. It's up to 2.8, which is not correct. You need to change that to E. Okay, when you do your calculation, when you do integral values, you need to go for 1.2 to E, not to 2.7, 2.8. If you go to 2.8, your value is definitely incorrect. And I find a lot of incorrect values. I think that's because of this. And a lot of you define the function wrong, which is a very careless mistake. Shouldn't make that mistake there. X log EX, well, I will recommend you to put a times in between the X and log EX when you type that into calculator in case there's something went wrong. And most of us figured that out in the end, so I have checked your answers, not much problem for example 3. For example 4, we have worked out P is 18 to the power of a third, and not much problem for that. Okay, so that's what we have learned yesterday. Well, basically it's area under the curve, proof density function, sketching density function graph. 6 things we need to talk about, like probability. We have finished that one, like we have finished number 1 yesterday. And today we talk about the rest of the 5 things: the expect values, standard deviation, variance, mode, and median. Okay, mode and median. We start from the easiest two. Okay, what is the mode? Okay, easiest one is the mode. Well, mode needs to see the graph. Okay, for the mode in this question, we no longer look at probability, because you know at any point the probability will be 0, right? For density continuous random variable, I said probably x equals to 3 is 0, because there's no area for that line 3. Whether you include the endpoint or you don't include the endpoint, you will have the same probability, because at one point that will be 0. That is the difference between continuous random variable and discrete random variable. Discrete, when you include the endpoint or you don't include the endpoint, they will make a difference, like you have that value or you don't have that value. This is different. But for continuous, it is the same. So therefore, I cannot find a point, like what is the probability and whether it's the highest one or not. Therefore, we look at the graph. The highest point, the absolute maximum will be your mode. Okay, the absolute maximum will be your mode. So For example, this one, the mode will be this x value because the highest point is here, is the x value of that point. Again, it's still the x value, not the fx value. So it's the x value of the highest point. Well, if this one is the turning point, so I can find f dash x equals to 0. Well, if you see the graph, I need to find f dash x equals to 0, use derivative to find the maximum. But for this one, if you see a graph is just strictly increasing, okay, it's just strictly increasing. Well, I don't need to find the diff value. This is the highest point, then the x value is the mode. Well, same as this one, the highest is from this is a strictly decreasing function. So left hand side, that point is the mode. So mode is very easy. You just need to sketch for it and look at which one is the highest point, and then you can work that out. Mode is easy. Median. Well, median, what is median? Median is where is your 0.5, where is your half, like half probability, contains half of the probability. So what all I need to do is from integral lower bound to m is your median of the density function dx, that can give you a half, which is 0.5. Okay, that gives you 0.5. So where is 0.5? From the lowest point until where give you 0.5. So for that area is 0.5. So if you think about, well, this one, well, the symmetrical quadratic, if that's 0, that's 2, then 1 will be my median. And also 1 is the mode. Okay, also 1 is the mode because it's the highest point. This is a quadratic. Well, you have 0 and 2 is your x-intercept. The middle must be 1. So you exactly cut the area into a half and half. So 1 will be the median. And at the same time, 1 is the mode as well. Okay, so it's just put that into calculator to solve. Okay, you solve for your median. Solve for your median. So your median must be in between the lower bound and upper bound, like the given domain. Okay, median mode is easy. Next one, we need to talk about the complex one, which is the expect value. Okay, expect value. Remember the notation we have for discrete. Discrete random variable, we have expected x equals to the sum for all the possible x. You use the x value times the probability of x, and then you add them all together. So it's the sum of that. For expected gx, what you have done is you sum all the x with the gx. Well, you find all the gx values and times the probability for that x. And sum all of that, all the values together, that will be your expected gx. Well, so therefore we have expected x squared will equals to sum of all the x squared times the probability of x. So that's for discrete random variable. Okay, that's for discrete random variable. We use the table and we times them vertically and adding them. It is very, very, very similar to continuous random variable. We almost use the same formula here. Okay, we almost use the same formula. The sum, okay, remember when we teach integrals, when the sum, like you're not summing finite numbers, you're trying to sum infinite many numbers, what the sign will become, like that sum sign. Integral, right? When we do, like, remember the rectangle thing? We're trying to sum all the rectangles, and when we decrease the x, into almost 0, we have infinite many rectangles to sum. That sum sign becomes an integral sign. Okay, that sum sign becomes integral sign. So therefore, here see this mu here. What we have exactly, almost exactly the same thing. X times fx. Well, originally it's px. Now we don't have px. We don't have probability, but we have density. So it's x times with the density. Before it's a sum sign, but it's now infinite many numbers, that becomes integral sign. Okay, that becomes integral sign. And with, well, before it's summing all the x values. Now again, we're trying to integral all the x values. So we integral, I put here negative infinity to positive infinity, but you need to adjust that for your given domain, like the lower bound to upper bound. Like it's not negative infinity to positive infinity. Like you need to adjust that to given domain. Well, this one and this one needs to change to domain. Okay, what is the domain? You change that to domain. And therefore, what is expected gx? Expect gx is just gx times the fx, and we integral that from the given domain, like lower bound to upper bound. So it's exactly the same thing. Instead, we sum all the things, now we integral that, because integral means the sum of all the values for infinite many numbers in between a to b. So same formula. So same formula. If you can remember the discrete one, like the continuous one, you just change that to the infinite many sum. Okay, so we just integral. Before we have px, now we don't have px, but we have fx. So change the px into fx, and that will give you the same thing. And if we try to find expected x squared, okay, we need expected x squared, because expect x squared can help us to find the variance. So we find expected x squared is integral from, well, given domain of x squared times fx. X squared times fx. And dx. Okay, that's my expected x squared. Well, if you're trying to go for expected 1 over x, that is just integral of the given domain 1 over x times fx dx. Very easy. You just change the formula into the integral, and you can antidiff that. That will give you the expected of that value. That formula still works for continuous random variable. Well, that is always true. Expected x plus b, it is still a expected x plus b. So if you find the continuous random variable expected x, that still works. Okay, that still works. So not surprisingly, we will have variance ax plus b is still equals to a squared variance of x. Okay, that doesn't change. SD ax plus b, that will still give you absolute a as dx. That's all the same as before. That formula doesn't change. Can you see the actual formula doesn't change? It's how you calculate the expected x changed. The only thing changes the method you calculate expected x. All the formulas stay the same. Okay, all the formulas stay the same. It's the only different thing is how to calculate expected x. It's a little bit different compared to before. But it's, as I explained, it's basically the same. You just change the sign to infinite many, and then everything is the same. Okay, so that's expected x. Okay, after we know what is we know the discrete one, we can find out the continuous one. And now we look at the variance. Well, variance doesn't change. Well, the two formulas for variance still here. Look at those two formulas. Well, there are two formulas. The second one comes from the first one. The first one said expected bracket x minus mu squared is how much gets spread of that x compared to your mu. Well, because expected gx equals to integral gx times fx, therefore, we will have this formula here. Well, if you have your calculator, you can directly enter that in. When you know your mu, put that in, and you can work out your variance value, variance value. Because your x minus mu squared, mu is a number. Okay, because you have worked out mu already, so mu is a number. So it's, for example, x minus 2 squared. So because expected gx equals to integral gx times fx, so the gx is x minus mu squared, and then we times fx, we integral from the lower bound to the upper bound. That will give us the variance. That will give us the variance. I'll show you an example how to use this one later. But I think we should get this now. Like expected of a formula, that formula just times with the fx, and then we integral that. Also, we still have expected x squared minus mu squared. That is still the formula for variance. As I said, formula doesn't change. It's only the way we calculate changed for continuous and discrete. That's the only thing changed. So therefore, expected x squared minus mu squared. Expected x squared will be x squared times fx dx. That's the thing I have right here. So that is your expected x squared. And your mu is just that, x times fx. X times fx, integral that, and then we square that value. That is the value of mu. So we have this formula here. Okay, still have two formulas to calculate variance x. Okay, one is expected x minus mu squared. The other one is expected x squared minus mu squared. Well, standard deviation is still the same as square root of variance. Nothing to talk about that. If you can find out the variance, you can work out the standard deviation by square root that value. And the formula is still the same for this one. Okay, still the same. Okay, the next thing we want to talk about is only in continuous. It is called the quartiles and percentiles. Okay, so what is quartile? What is the percentile? So quartiles and percentiles are both define the value of a random variable. So it is a value of a random variable. So x equals to what? It asks you x equals to what? Below which give you the proportion of the distribution false. The only difference, well, basically they're the same thing. The only difference is quartile is the probability value expressed as a decimal. Okay, quartile is a decimal, and percentile is a percentage. Okay, so we will say 0.6 quartile or 60th percentile. Okay, 0.6 quartile or 60th percentile, that's the same thing. So what is 60th percentile? If I just sketch a continuous density function, okay, I have sketched that one. That can be a cubic. So we have x and fx. Okay, we have 0 here. We have 0 here. So what is 60th or 0.6 quartile? What is 60th percentile? It is from the left, cumulate until a point A. That area give you 0.6. So A is the 60th percentile or 0.6 quartile. So you always cumulate from the left. So cumulate from the left until a point. That area can give you 0.6. Well, if you need 70th percentile, that's 2.7. If you need 80th percentile, that area needs to be 0.8. So it's always from the left until a point on the right. That can give you the given area. Okay, that can give you the given area. Or 60th percentile is 0.6. You know that. So how we can solve for that? We can solve integral from, well, let's say that point is -1, that point is 5. So we can solve that as -1 to a. Okay, -1 to a of this fx function, dx. And that can give me 0.6 of the area. Well, the question used k, so I will change that to k. Okay, you solve for k. So you put that into the calculator, you can solve for k. So from the lower bound until that point, that area gives you 0.6. And what is that k value? You can work out that by calculator. So this is the quartile and percentile question. Okay, now we have talked about the 5 things: expected value, variance, standard deviation, mode, and median. And also we talk about what is a definition for what is quartile and percentile. So it's another formula page, okay? Same as chapter 13, the second last page is a pure formula page, and it is exactly the same. You can see the format is exactly the same. So it's the same kind of thing we use for continuous random variable. And what you should realize is everything doesn't change. The formula stay the same. The only difference is how we calculate expected x and expected gx. That's the only thing changed. Okay, so from page 6 until page 10. Okay, 6, 7, 8, 9, 10. Those 5 pages, they are all questions just asking what, well, some of them are just pure questions like what is the exact value, what is the variance. Some are like wording questions, give you a context, how to calculate that. I'll just show you one example. Let's do one example. I'll do this one with you. I'll do page 10, the last question here. Okay, I want to do this one with you. Okay, page 10, example 10. I want to do that one with you. Let's add one more question to that. First of all, prove that is a density function. Okay, the first one is prove that is a density function. So, example 10. This question is very special. It's very important here. We can see our domain. Very interesting question, okay? Our domain is 0 to infinity. You know, normally we should go for from here to here. That area. Give me exactly 1. But now I want to go infinity. Well, y still can go infinity and still have area of 1. That's what I want to prove now. Like, it's very interesting because you can think about that's infinite many area like under the curve. But why that still works? Let's do that. So let's add a question like proof fx is density function. Okay, let's sketch that first. What kind of graph is that one? What's the name of the function? Exponential? Okay. Which way it should go? Increasing or decreasing? Under the asymptotes or below the asymptotes? Above the asymptotes? Increasing or decreasing? Decreasing. Okay, good. So A, we sketch for that. Because this need to be above the x-axis, so I just sketch that. And I have my fx here. Well, that's I don't say that's A. Let's just prove that. Okay, what's the starting point? When x equals to 0, y equals to what? 0.3. So when x equals to 0, e to the power of 0 is 1. That gives you 0.3. You can take 0, so I will have this point here. Where is the asymptotes? Y equals to 0. Okay, my asymptotes only on the right hand side because the domain is x greater than 0. Plus is decreasing function, so I should have that. Okay, this is my graph. Is that graph finished? What's left? 0. Okay, so I should have an open circle here, and I should sketch 0 on that side because I need to cover all the x values. If there's no domain given, so the rest of that must be 0. So it's not possible to have x less than 0. So we should have this horizontal line here, and also this curve here and the asymptotes here. So what I'll label is y equals to 0. This point is 0, 0.3. This open circle is 0, 0. And the rest of that is just 0. Okay, you must show everything to get a full mark for this density function. Okay, 1, 2, 3, 4. 4 things you need to label. Okay, next thing. I want to prove this is a density function. Okay, I want to prove this is a density function. So I have shown that step number 1, fx is above 0 for Ox. Okay, when I sketch it, I can make that statement because my graph has shown that it's all above the the x-axis or equals to the x-axis. The second one is I want to show the integral from 0 to infinity of that function equals to 1. Well, it's not equals to 1 now. I want to show that equals to 1. What's the integral value for this one? What's the integral for that? What's the integral for that? E that? Sure? It's not right. Missing something. Negative. Okay, you divide by negative 0.3. So you divide by a, so you divide by negative 0.3. So it's negative e to the power of negative 0.3x. So that's the antiderivative value. And I want to go for 0 to infinity. So I sub that in. Okay, I sub that in. So that's negative e to the power of negative 0.3 times infinity is negative infinity, right? It's just, well, 0.3 times a really, really large number, still quite large, it's still negative infinity. That minus negative e to the power of 0 when you sub 0 in. What's e to the power of negative infinity? If you look at exponential graph, when x equals to negative infinity, what y approaching to? 0. So this value is just 0. Okay, so we treat that is just a 0. So that is a 0 minus a negative 1. So that's equals to a 1. So that's why it's still a density function here. Because e to the power of negative, it's not exactly 0, but it's good enough to assume that's just a 0. So we treat that as a 0. Therefore, we have 0 minus negative 1, and that is just a 1. Okay, you can think about e to the power of negative 10,000, e to the power of negative 1,000,000. You can put that into CAS, and it's a really, really small number, 0.00000 something. And when I increase that number, it's good enough to say it's approaching to 0. And then we treat that as a 0. So therefore, that's why when I still increase to infinity, I can still say the area just one end of the curve, because it's good enough to assume that's just 1. Okay, then I have shown that is a probability density function because it's all above or equals on the x-axis. And second, I have shown that the area under the curve is just 1. So all good for that one. Okay, next one, calculate the mean. Well, when I do this type of question, I will like to define the function, but because my calculator mode is in the auto mode, so what I will do is I will put that into fraction form, negative 3 over 10.3, right? Times x, e to the power of negative 0.3x. Control VAR, I said that's fx. Define that. So A, find the mean, which is expected x. Okay, find mean, which is expected x. So the expected x equals to integral of 0 to infinity x times fx dx. And that equal, well, I can't do this by hand. So integral 0 to infinity x times f bracket x dx. Okay, I have 10 over 3. So if you put that in CAS, that gives you 10 over 3. B is asking for median. Okay, median is 0, well, from the most left hand side to m. M is the median. Well, we don't have x times fx, we just say fx. You need to distinguish between expected value and calculate probability. So now I want the probability from 0 to a point to be 0.5. Okay, to be 0.5. So 0 to m of fx, not x times fx. So it's just the area under this curve will give you 0.5 from 0. And I'm solving for m. M equals to menu 3,1 integral 0 to, I can't use x, I needs to use m. And of the function fx dx that can give you 0.5. Well, instead of saying 0.5, I'll say 1/2. See if I can get exact. I just don't think I can get exact. Comma m. Okay, solving for m, comma m. So 0 to m dx equals to 1/2, and so for m. Well, I can have exact value. See, my m is 10/3 log E2. Okay, 10/3 log E2. If you keep all exact, I should have 10/3 log E2. Well, instead of putting 0.5, I'll put 1/2 in. Okay, and so for that, I will have everything in exact. If you can have exact, then everything will be exact. So that will give you 10/3 log E2 for the median. What is the mode? Yeah, so what's that? 0. So mode is 0. The highest point is 0,3. So the x value of the highest point, which is 0. Okay, D is asking for standard deviation. Well, to find standard deviation, we need to find what first? Variance. Okay. There are two formulas for variance. I'll show you both. Okay, I'll show you both. The first one, variance x, is integral from 0 to infinity. X minus mu. Mu is 10/3 squared times fx dx. That's the first way I can directly get the variance without finding the expected x squared. So it's x minus mu, so it's x minus 10/3 squared. That's the gx. Gx times fx, because variance x is expected x minus mu. Mu is 10/3 squared. So expected gx, I put gx here times with fx. I should have the value directly. So that equals to integral 0. I will copy this down. All disappear. Do I still have my fx? Yes. Okay, I still have my fx. Integral 0 to infinity. Bracket x minus 10/3 squared times fx dx. Okay, that's just my variance value. I just use one line to work out the variance, which is 100/9. Okay, which is 100/9. That's the first method. Okay, that's the first method. My second method is use variance x equals to expected x squared minus mu squared. So I want to find expected x squared first. Expected x squared equals to integral 0 to infinity x squared times fx dx. Still use the same formula. Okay, still use the same formula. X squared times fx. That equals to, well, I can copy this down. I can change that to a 0. So it's x squared times fx. Yeah, put more here. So that is 200/9. Okay, that's x squared times fx from 0 to infinity. That's 200/9. X squared 200/9. So variance x equals to 200 over 9 minus mu is 10 over 3 squared, which is 100 over 9. And I will have 100 over 9. That gives you the same result as the first one. Okay, the top line. Still, you have the same thing. You just use two different formulas, but you should achieve the same thing. One is directly use x minus mu squared, and the second one I use expected x squared minus mu squared. So s dx equals to square root of 100 over 9. That's 10 over 3. That is 10 over 3. All right, next one, E. Okay, E, when you see that notation, what's the guessing probability? E. Mu minus 2 sigma, mu plus 2 sigma, 95%, okay, 95%. But again, this one asks us to calculate, okay, to calculate. I'll just use the space here. Mu minus 2 sigma equals to 10 over 3 minus 2 times 10 over 3. That's the same thing, right? That's the same thing. 10 over 3 is the mu, sigma is 10 over 3 as well. So it's 2 that, and that equals to minus 10 over 3. 1 10 over 3 minus 2 10 over 3 is minus 10 over 3. Mu plus 2 sigma is 10 over 3 plus 2 times 10 over 3. Well, the SDX is the sigma. Okay, the SDX is the sigma. That equals to 10. So I'm trying to calculate the probability of minus 10 over 3 greater equals to x greater equals to 10. So I change the mu minus 2 sigma, 10 plus 2 sigma. How I should adjust these values? How I should adjust it? What's the domain? 0 to infinity. So which value or which values should be changed? The left-hand side needs to be changed. So that needs to be changed to a 0 to 10. Okay, it's not satisfy your domain. So what you need to do is actually from 0 to 10. You need to be aware of your domain when you do continuous random variable. Okay, the domain is so important. Well, for binomial, you still need to be aware of your domain. You still need to change it to the inside integer values. Okay, the inside integer values. So after that is just 10, 0 to 10 of fx dx. Right, it's just 0 to 10. And the area under the curve from 0 to 10. Find the probability. And let's see, the value is 0 to 10 of fx. Yes. Okay, that's the probability. And I can go Control Enter to see it's very close to 95%. Okay, it's very close to 95%. Well, if I expand this is a 1 minus 1 over e to the power 3. So that equals to 1 minus 1 over e to the power 3 is approximately 0.95 if I give 2 decimals. Okay, so if you expand the formula e3 times e negative 3, that's a 1, and e to the power minus 3 is 1 over e to the power 3. So it's 1 minus 1 over e to the power 3. Okay, from 0 to 10, give you approximately 95%. Okay, so that is, again, we use binomial to prove in between two standard deviations very close to 95, and I use a continuous random variable to prove in between two standard deviation is very close to 95% as well. So this is kind of, it's not a rule, it's approximately 95%. It's just something in common for all the distributions. So within two standard deviation, it covers most of the probability, which is 95%. Okay, any questions for that? It's very straightforward, pure calculation, substitute. After we finish all the probability, I'll give you a summary sheet on all the 4 different chapters, the expect value, variance, the 6 things we're trying to work out. I give you a summary. You can make a summary by yourself as well, but I'll wait to finish normal first. So what I want you to do for today is Tuesday, right? So for Thursday, maybe Friday as well, I want you to complete everything before page 10, okay? Finish everything before page 10. So all the questions is all just talk about expect value, variance, standard deviation, mode, median, and the probability. So you bring your notes to class and then working on those questions. Give your one lesson to consolidate all the things you need. Any more questions for today?